Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to talk on the module Quantum Confinement, Size Effects and Properties of Nanostructures under the paper Nanoscience and Technology First. So after completing this module, you will be able to learn first electronic organization of bulk semiconductors, second electronic transitions in bulk semiconductors, thirdly electronic structure of the semiconductor nanostructures, that is top down approach. So students, let us start with a basic introduction about the module. This module discusses the evolution of quantum size effects and their influence on the electronic structure of the semiconducting nanostructures. Quantum confinement effect has been introduced via two approaches: top to down and bottom to up. So quantum confinement refers to the spatial confinement of electrons in a nanomaterial rather than the free existence within the bulk materials. The effect of spatial confinement are different for unlike materials and their properties because it varies with the characteristic length scale of the property that is eventually shaped by a material's structure and composition. The significant length scale here is the exciton or electron hole pair, Bohr radius A0, a dimension that describes the spatial extent of the excitons in a semiconductor, and it is in between 2 and 50 nanometers based on the type of material. This spatial extension of the excitons inside the semiconducting nanostructures result in the effect of quantum confinement. So appreciating its cause and influence on electronic structure of the semiconductor nanostructure is a vital aspect of nanoscience. So to appreciate the influence of quantum confinement phenomenon on electronic configuration of the given nanomaterial, the knowledge of electronic structure of bulk material is a prerequisite. Electronic organization of bulk semiconductors. Contrary to an unbound or free electron moving in vacuum, the electrons within the semiconductor encounter the periodic potential produced by atoms of the crystal lattice. So for simplicity, we begin with the description of a 1D hypothetical crystal expressed by the Hamiltonian as H equal to H naught plus Vx, which is equal to minus H cut square by 2m del square by del x square plus Vx. Now here V is the periodic potential caused by the lattice, and H0 denotes the kinetic energy operator. The potential V has periodicity over lattice spacing A, that is Vx equal to Vx plus A, signifying that the Schrödinger equation with translation of a wave function psi x by the distance A multiplied by psi x plus A. So it can be written as Schrödinger equation with translation of a wave function, which leads to this following equation, that is minus h cut square by 2m del square by del x square psi x plus A plus Vx psi x plus A equal to E psi x plus A. E after translation over A. This means that wave function psi x and psi x plus A will only vary by the phase factor. So wave functions obeying this condition, along with being the eigenfunction of the equation 2, may be given as psi block as a function block k as a function of x equal to exponential iota kx ukx. Now where k is 2 pi by lambda is the wave vector, and ukx is a periodic function having the periodicity of lattice constant, that is ukx equal to ukx plus A. This resultant wave function is termed as the block function, representing the plane wave exponential iota kx, modulated with the periodic function ukx of valence electrons towards periodic lattice potential caused by the lattice. So translating the block function over A yields psi block k as a function of x plus A equal to e to the power iota ka psi block k as a function of x. This relation demonstrates that after translation over A, the wave function only differs by the phase constant x, having continuous energy levels described by the dispersion relation Ek equal to h cut square k square by 2 m naught, where m naught represents the mass of free electron. So the first figure A shows us the variation of energy versus the k vector. The lattice produced periodic potential, resulting the significant changes in electronic dispersion relation. So the electrons which are propagating through lattice having wavelength from A get barely disturbed, and hence their energy is comparable to the free or unbound electrons. Nonetheless, as electrons' wavelength is double the lattice constant, or else when k equal to pi by A, these electrons get reflected from the crystal potential. These are nothing but Bragg reflections and produces standing waves represented with a linear combination of k equal to minus pi by A and k equal to plus pi by A plane waves. These standing waves are psi plus block and psi minus block are alike apart from the displacement of A by 2 in x. This results in considerable disparity in energy of these standing waves. since first wave concentrates electronic probability at ions, thereby reducing the potential energy, while second one amasses the probability of electrons in the middle of the ions. Therefore, because of the disparity in electron charge distributions, these standing waves possesses dissimilar energies at identical k value, resulting in an energy gap within the dispersion relation. Lattice periodicity initiates the Bragg reflections at many k values, where k is n pi by a and n is the integer, resulting in the dispersion relation having several energy gaps, and this is shown in this figure B. Now alternatively, block function is periodic in k, implying that the wave functions having k values differing by 2n pi by a are same may be obtained from the previous equation 4. So this can be understood as the following, that is value of the phase e to the power iota kx at ions x equal to qa, where q is integer, is equal at k and k plus 2 pi by a, thereby portraying similar physical situation. Accordingly, energy dispersion relation can be limited to the k values in minus pi by a to k to plus pi by a window, and the values of higher k may be folded in this zone by deducing 2 pi by a from the k value. So this resultant interval in 1D is the first Brillouin zone within which the energy dispersion may be plotted. So this is detailed shown in the figure C. So the restriction of the dispersion relation within the limit minus pi by a to plus pi by a results in the occurrence of energy bands, and each k value possess many related energy value, and it can be considered as the overtones. So gaps occur between the different bands at k equal to 0 and k equal to pi by a. So the electronic structure of 3D crystal may be described on similar to the 1D case. Let us now discuss about the electronic transitions in bulk semiconductors. Valence band in semiconductors is full, whereas conduction band remains vacant. So an external perturbation can promote an electron from valence to conduction band. For example, absorption of a photon with the energy equal to or greater than the band gap. The valence band to conduction band transition of an electron can be depicted like a system where conduction band has one particle while valence band has several many particles, which is devoid of one particle. So this becomes many body system and can be simplified by expressing many interacting particles with the least possible non-interacting particles termed as quasi-particles. So we start by introducing the quasi-particles in valence band, that is hole, that can be associated with a group of electrons present in valence band, out of which the electron was taken out. Electron in conduction band can be defined by the charge E minus, electronic spin S equal to half, and an effective mass Me star. while these variable charge 2e plus s equal to half plus half, and the mass is mh star respectively for charge, spin, and mass. So, as they possess charge, the electron and hole are described as the charge carriers. Here, effective mass takes into consideration the interactions between the particles and the lattice and therefore reflects the increase or decrease in the mobility of the particle within the semiconductor with reference to that of free electron in a vacuum. So, a larger effective mass implies such interaction with the lattice, which slows the particle, while greater carrier mobility corresponds to lower effective mass. Conversely, the effective masses can point towards the spatial limit of the carrier wave function because delocalization degree varies inversely with the effective mass of charge carriers, meaning that the lighter carrier delocalize more. So, as the electrons and the holes are oppositely charged, they interact by the Coulombic potential, creating an electron hole pair, which is expressed by the quasi-particle or exciton. The creation of exciton involves some minimum energy, which can be written as E equal to h cut omega equal to Eg plus E kinetic plus H kinetic, where Eg is the fundamental band gap of the semiconductor. E kinetic and kinetic are respective kinetic energies of electron and hole. Additionally, momentum conservation requires h cut kcb equal to h cut kvb plus h cut k photon, where kcb and kvb are respective wave vectors of elevated electrons in conduction band and holes in valence band. Since the momentum of photons is negligible, so the condition kcb and kvb must be satisfied. Thus, in the absence of external disruptions, the transitions only within the same k values can take place, which is shown in this figure, which represents the transition of an electron from valence band to conduction band within a direct band gap semiconductor as a result of photon absorption. The exciton energy is given by the dispersion relation, that is En equal to Eg minus Ry star by n square plus h cut square k square by 2 me star plus mh star. So the second term in this equation consists of hydrogen-like energy levels, where Ry star denotes the exciton Rydberg energy corresponding to the ionization energy of lowest hydrogenic state. Third term is the kinetic energy of exciton's center of mass movement with exciton wave vector k. Kinetic energy term looks like the dispersion curve of the free electron, except owing to the difference that it incorporates the effective mass of the exciton. This term stems from the fact that the interacting electrons and holes might be expressed as distinct particles interacting by a Coulombic potential. So Hamiltonian, similar to that of the hydrogen atom, can be employed to estimate the energy of the exciton, wherein the effective mass of exciton substitutes the free electron mass m0. So analogous to the hydrogen atom, distance of an electron from the hole within the exciton is described as the exciton Bohr radius A0, which is given by h cut square epsilon by E square multiplied by 1 by me star plus 1 by mh star, where me star and mh star are the respective effective masses of electron and hole. E is the electronic charge and epsilon is the semiconductor dielectric constant. So exciton Bohr radius gives an important length scale to represent the spatial extent of the excitons in a semiconductor varying from 2 to 50 nanometer, relying on the semiconductor. Note that the band gap and the Bohr radius A0 of the semiconductor are correlated such that the materials with wider band gaps have smaller A0. So let us now discuss about the electronic structure of the semiconductor nanostructures. Electronic structure of a semiconductor nanocrystal demonstrates strong dependence on the size of the nanocrystal. The effect called quantum confinement may be described by two approaches. So that is the top-down and the bottom-up, where the top-down approach treats nanocrystals being tiny pieces of the semiconductor material, wherein exciton is confined spatially. While in the second approach, that is bottom-up approach, it is considered as the molecular or quantum mechanical methodology, wherein the nanocrystal is constructed atom by atom into a progressively bigger molecular cluster, which ultimately grows into the bulk crystal. So we will discuss both these approaches in the subsequent sections. So let us first start with the top-down approach. In this method, block functions relating the semiconductor bulk properties comprising the band structure and valence zone are maintained, except the multiplication with an envelope function, taking care of spatial extension of the charge carriers and exciton in the nanocrystal. That is, psi total is equal to psi block multiplied by psi envelope. Now the entire wave function is the psi total, therefore combines this block function, that is psi block, with the envelope function, that is phi envelope, which is the confinement of the charge carriers within the nanocrystal. So phi envelope is therefore a solution to the Schrödinger equation for a particle in a box problem. So in a 3D box of dimension small l, the wave function will be the product of the sinusoidal functions in x, y and z directions. So for isotropic confinement across all the directions, nanocrystal is characterized as spherical potential box, for example, a quantum dot. So the eigenfunctions are expressed as a product of spherical harmonics y theta phi and a radial Bessel function r. So phi envelope theta phi r equal to y n lm theta phi multiplied by r as a function of small r. So envelope function has high similarity to the wave functions depicting electron in the hydrogen atom. There, the potential encountered by the electron is decided by a positively charged proton, or Vr is approximately 1 by r, whereas a quantum dot does not have such positively charged center. Alternatively, electrons come across a spherical potential well with diameter d, wherein Vr equal to minus V naught for r less than d by 2, while Vr equal to 0 at other places. So putting equation 11 into the Schrödinger equation provides the solution for the discrete energy levels of the spherically confined electron. So we have ENL confined as a function of capital D equal to 2h cut square chi NL square divided by m star d square. Now here m star is the effective mass of electrons or holes. Chi NL represents the solution of Bessel function and are absolute values relying on or increasing with the principal n equal to 1, 2, 3 and azimuthal L equal to 0, 1, 2, 3 analogous to SPD orbitals quantum numbers. So this is depicted in this figure, which shows the schematic of the quantum confinement effects on electronic structure of a semiconductor. In the first figure, we have a bulk semiconductor. The second one represents the three lowest electron, ENLE, and whole ENLE energy levels in a quantum dot, with broken lines showing the corresponding wave functions. And the third figure shows a semiconductor nanocrystal. So the minimum energy level, which is described by n equal to 1 and L equal to 0, demonstrates the symmetry of the 1s orbital of hydrogen atom. An important consequence from the difference in the potential of a quantum dot and hydrogen atom comes out to be that there is no restriction on L azimuthal quantum number. With respect to n, that is the principal quantum number, in a quantum dot, whereas in the case of hydrogen atom, the two are related by the relation L less than equal to n minus 1. Thus, next energy level in the quantum dot is expressed as n equal to L equal to 1, 1p level. Third level is n equal to 1 and L equal to 2, 1d level. Fourth is 2s level, n equal to 2 and L equal to 0. So as the envelope wave function of the lowest lying energy levels is atomic-like, the quantum dots are frequently regarded as artificial atoms. So the band gap of a quantum dot is therefore the sum total of the bulk band gap e.g. 0 and the confinement energy E confinement of electrons and holes. So Eg total will be equal to Eg naught plus ENL confined, which is equal to Eg naught plus 2 h cut square chi NL square by Me star D square plus 2 h cut square chi square NL by Mh star D square. It is notable that the energy levels of electrons and holes are treated independently in this equation, implying that the Coulombic interaction between them is not strong enough to keep them bound as exciton anymore. So this approximation works only for strong confinement system, which is valid for nanocrystal. In this region, confinement potential exceeds the Coulomb interaction. And it may be noted that Coulomb interaction is much larger in a quantum dot than in the bulk crystal. So at R less than, very much less than A naught, the kinetic energy of the charge carriers is even now much greater than their Coulombic interaction. Thus, electron and a hole can no longer be interrelated and may be considered individually. So, if the nanocrystal radius r greater than A naught, then the increment in the exciton energy is because of the quantization of excitonic center of mass movements. So, the exciton can be expressed as a typical particle in a spherical potential with its discrete energy levels described by the relation identical to equation 12 only by substituting electron hole effective mass with exciton effective mass. So energy level shift in the case of weak confinement region is very small than in strong confinement case. The quantum confinement effect is generally not apparent for the dimensions greater than 2 to 3 times of. So now, if Coulombic interaction is also considered, then the band gap of quantum dot will be given by Eg equal to Eg naught plus h cut square pi square by 2r square multiplied by 1 by Me star plus 1 by Mh star minus JEH plus EH pole plus EE pole minus 0.248 ERY star, where JEH is the actual Coulombic interaction between the electron and the hole, and it is 1.786 E square by epsilon 1 R. EH pole and EE pole represents the respective self-polarization energies for holes and electrons, and it depends on E square by R and the dielectric constants of quantum dot, epsilon 1 and also of the surrounding epsilon m. E star Ry represents the exciton Rydberg energy and reflects the spatial correlation between the electron and the hole. So this figure shows the schematic of the quantum confinement effects. That is, the semiconductor band gap increases with decrease in size. Also, the energy levels becomes discrete at band edges, and energy difference between the band edge level increases with reducing size. The bottom image shows the fluorescence of 5 dispersions of cadmium selenide quantum dots of differing dimensions under UV excitation. So, students, the previous equations describe the two vital outcomes for quantum confinement, that is, which we have already described, that is, band gap increases with reducing dimensions, and discrete energy levels appears at the band edges of both conduction band and valence band. It is noteworthy A0 gives a suitable length scale for evaluating the quantum confinement effects on the semiconductor nanocrystal properties. Confinement sets to influence the exciton wave functions as soon as the size of nanocrystal reaches A0. This implies that quantum confinement begins at different nanocrystal sizes for different semiconductors, as A0 varies broadly within the semiconductor materials. It is to be noted that A0 and bandgap Eg are interrelated. On the contrary, insulators, they are described by extremely confined excitons and therefore possess very short A0 and thus gets influenced by the quantum confinement effects for the sizes already in the cluster region. So students, let us now summarize what we have learned in this module. Firstly, we discussed about the electronic organization of bulk semiconductors. Secondly, the electronic transitions in bulk semiconductor were discussed in detail. Thirdly, the electronic structure of the semiconductor nanostructures, that is, top down approach and bottom up approach, were discussed in detail. Thank you.